Look up at the night sky. What do you see? A scattering of stars, perhaps a planet or two, the faint glow of the Milky Way stretching across the darkness. But what if I told you that every point of light out there is more than just a distant sun? Each one is a time capsule, a messenger carrying stories from the deep past, some so old they predate the Earth itself. The universe has a memory, and it's written in the language of light, radiation, and gravitational waves. For centuries, humanity has gazed at the cosmos, unaware that we weren't just observers, we were detectives, piecing together clues left behind by events that unfolded billions of years ago. Think about the last time you heard an echo, a shout bouncing off a canyon wall, returning to you seconds later. Now imagine that echo took millions of years to reach your ears. That's what astronomers are listening to when they study the faint whispers of cosmic microwave background radiation, the afterglow of the Big Bang, or when they capture the ghostly remnants of a supernova, a star's final act playing out in slow motion across the galaxy. These signals aren't just static, they're fragments of a grand narrative, one that tells us where we came from and where we might be headed. This is the heart of the cosmic memory, a quest to decode the universe's oldest messages. From ancient civilizations who mapped the stars with nothing but naked eyes and stone monuments, to modern scientists using telescopes so powerful they can see back in time, we've always been driven by the same question: what is the cosmos trying to tell us? The answers are stranger than fiction: dark matter weaving invisible webs between galaxies, black holes singing in frequencies we're only now learning to hear, and the possibility that the universe itself might be keeping secrets we've yet to uncover. So let's begin this journey together, tracing the echoes of the past to illuminate the mysteries of our present, and perhaps catch a glimpse of the future written in the stars. The cosmic memory isn't just a poetic metaphor, it's the universe's way of keeping receipts. Every photon of light, every ripple in space-time, every faint whisper of radiation is a page in a cosmic ledger, recording events that happened long before humans walked the Earth. Take starlight, for example. When you gaze at Sirius, the brightest star in our night sky, you're not seeing it as it is today. You're seeing it as it was 8.5 years ago, because that's how long its light took to reach us. And that's just our celestial backyard. The Andromeda Galaxy, that fuzzy patch in the sky, is a 2.5 million year old snapshot. We're not just looking across space, we're peering back in time. But light isn't the only messenger. Gravitational waves, those subtle vibrations in the fabric of space-time predicted by Einstein, carry stories of catastrophic collisions between black holes and neutron stars. When scientists detected these waves for the first time in 2015, they weren't just witnessing a distant event, they were eavesdropping on a conversation that began over 1 billion years ago. Even the cosmic microwave background, that faint static hiss from the dawn of time, is like the universe's baby photo, capturing its appearance when it was just 380,000 years old. These signals are more than data, they're fragments of a cosmic autobiography waiting to be read. What makes this memory so extraordinary is its permanence. On Earth, memories fade, artifacts crumble, and even digital data degrades over time. But in the vacuum of space, information can travel undisturbed for billions of years. A single photon from the early universe racing through the void carries its story perfectly preserved, no distortion, no edits. It's as if the cosmos itself is an obsessive archivist, cataloging every event with impeccable precision. And now, with tools like the James Webb Space Telescope and gravitational wave observatories, we're finally learning to translate this ancient language. We're not just studying the universe, we're reading its diary, one extraordinary entry at a time. Ancient astronomers didn't just watch the sky, they spoke its language. Picture a Babylonian scholar crouched over a damp clay tablet, carefully pressing wedge-shaped marks to record the exact position of Venus as it gleamed in the twilight. These cuneiform notes, dating back over 3,000 years, weren't just celestial shopping lists, they were meticulous diaries of the cosmos, tracking planetary motions with such precision that modern scientists still use them to study changes in Earth's rotation. The Mayans took it even further, carving their lunar and solar calendars into temple walls with mind-bending accuracy. Their calculations for the length of a year were off by just minutes compared to today's atomic clocks, achieved without a single lens or silicon chip. What's truly humbling is realizing these cultures saw patterns we often overlook. The Egyptians aligned the Great Pyramid so precisely that its corridors frame the pole star of their era, while the entire structure acts as a giant stone clock, its shadows marking equinoxes and solstices. Were these monuments just fancy calendars, or did their builders intuit something deeper about the universe's rhythms? The Dogon people of West Africa, for instance, recorded detailed knowledge of Sirius's invisible companion star centuries before telescopes could confirm its existence. How their oral traditions spoke of a dense, tiny star, heavier than all the iron on Earth, an uncanny description of a white dwarf, a star so dense a teaspoon of its material would weigh tons. These weren't random guesses. They were the result of generations watching, recording, and listening to the sky's whispers. The ancient Greeks called it astrotheology, the idea that celestial events were messages from the gods. But strip away the mythology and you find something remarkable, a universal human impulse to decode cosmic memory. Whether etched in stone, painted on tomb ceilings, or woven into oral epics, these records share a common thread. They treat the universe not as a static backdrop, but as a living narrative, its cycles and anomalies brimming with meaning. Today, we've swapped clay tablets for quantum sensors, yet the core quest remains unchanged. When a modern astronomer calibrates a telescope to hunt for exoplanets, they're walking the same path as a Mayan scribe tracking Venus's dance across the dawn. Both are translators of sorts, turning the universe's silent signals into stories we can understand. The tools have evolved, but the wonder, that's as ancient as the stars themselves. Light doesn't just illuminate the cosmos, it narrates it. Every beam traveling through the void is packed with information, like a cosmic telegram sent across millennia. When astronomers point their telescopes at a star, they're not just measuring brightness, they're deciphering a complex code written in wavelengths. This is the magic of spectroscopy, the art of reading light's hidden signatures. Picture sunlight passing through a prism, splitting into a rainbow. Now imagine that rainbow holds secrets, not just colors, but the very ingredients of the star itself. Dark lines streaking across that spectrum are like barcodes, each one revealing the presence of elements like hydrogen, helium, or even traces of iron forged in stellar furnaces. The implications are staggering. A single beam of starlight can tell us how hot a star burns, how fast it's moving, even whether it's cradling planets in its glow. Take the star Vega, for example. Its light, analyzed through spectroscopy, betrayed a swirling disk of dust, a telltale sign of planetary formation in progress. But the real mind-bender, some of the light reaching us today carries the chemical fingerprints of stars that died billions of years ago. When massive stars explode as supernova, they scatter their elemental guts across space. Those atoms eventually get recycled into new stars, planets, and yes, even us. Spectroscopy lets us trace that lineage, like reading the universe's family tree written in photons. Now, with tools like the James Webb Space Telescope, we're not just reading the cosmos's mail, we're decoding its diary. JWST infrared eyes peer through cosmic dust, catching light stretched and redshifted by the expansion of the universe itself. Recently, it spotted galaxies so ancient their light has been traveling for over 13 billion years, nearly the age of the cosmos. Their spectra revealed something astonishing. These toddler galaxies were already heavy with metals, elements that shouldn't have existed so soon after the Big Bang. It's like finding a sophisticated city in what we thought was an empty wilderness, but light isn't the only storyteller. The universe writes in invisible ink too. Radio telescopes eavesdrop on the faint whispers of hydrogen atoms, while X-ray observatories capture the death screams of matter spiraling into black holes. Every wavelength, from gamma rays to radio waves, is a different dialect in this grand cosmic language. And just as archaeologists piece together history from pottery shards, astronomers assemble the universe's epic from these scattered photons. The next time you look up at the night sky, remember, you're not just seeing points of light, you're witnessing billions of years of history streaming toward you in real time. Cosmic microwave background radiation isn't just an echo of the Big Bang. It's the universe's first cry frozen in time. Picture the cosmos as a newborn just 380,000 years old. Before that moment, it was a searing, opaque soup of particles, too dense for light to travel freely. Then, in a cosmic blink, space expanded enough to let photons break free, sending that first burst of light racing outward in all directions. Over 13 billion years later, that light still surrounds us, cooled to a faint whisper just 3 degrees above absolute zero. It's the oldest light we can see, a relic from when the universe was 1,000 times smaller and 1 billion times hotter than today. What's astonishing isn't just its age, but what it reveals. The CMB isn't perfectly uniform, it's mottled with tiny temperature variations, some as small as 1 part in 100,000. These imperfections are cosmic fingerprints, the gravitational footprints of dark matter clumping together, tugging at the young plasma. Think of it like dough rising. The denser regions became the seeds for galaxies, while the emptier stretches evolved into the vast voids between them. Without these microscopic fluctuations, gravity would have had nothing to grip, and stars might never have ignited. Scientists decode these patterns like archaeologists reading hieroglyphs. Satellite missions like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, revealing a wealth of information about the universe's composition, age, and even its fate. The patterns confirm that ordinary matter, the stuff of planets and people, makes up less than 5% of the cosmos. Dark matter and dark energy dominate the rest, shaping the universe in ways we're only beginning to grasp. But the CMB isn't just a relic, it's a time machine. Its polarization, a subtle twisting of light waves, carries traces of primordial gravitational waves, ripples from the universe's violent birth. Some theories suggest these ripples could be evidence of cosmic inflation, a fleeting moment when the universe expanded faster than light itself. If proven, it would mean the CMB isn't just a baby picture, it's a birth certificate signed in the aftermath of creation. The next time you tune an old radio to static, listen closely. About 1% of that noise isn't random, it's the CMB, the universe's oldest broadcast, still playing after all these eons. It's a reminder that the cosmos isn't just above us, it's in us, etched into every atom, every photon, every breath we take. We're not just observers of this memory, we're part of its story. Neutrinos are the universe's shadowy couriers, slipping through planets and stars like ghosts through walls. Billions pass through your body every second, leaving no trace, no heat, no light, no ripple. These nearly weightless particles, born in the nuclear furnaces of stars and the cataclysms of supernova, carry stories from places light cannot escape. Imagine a star collapsing in on itself, its core screaming with energy. While light struggles to break free from the chaos, neutrinos zip away at nearly the speed of light, untouched, unfiltered. By the time that star's final light reaches us, its neutrinos have already raced ahead, delivering their message millennia earlier. Detecting these phantoms requires ingenuity on an almost absurd scale. Take IceCube, a telescope buried deep in Antarctic ice, its sensors waiting for the rare moment a neutrino collides with an atom. When it happens, the ice glows blue, a phenomenon called Cherenkov radiation, revealing the neutrino's energy and origin. In 2013, IceCube caught neutrinos from beyond our galaxy, their energies so staggering that scientists traced them back to blazars, supermassive black holes firing jets of radiation across the cosmos. But here's the twist: these particles weren't just messengers, they were time travelers. Some likely began their journey when the universe was half its current age, their paths undisturbed by magnetic fields or dust. What makes neutrinos invaluable isn't just their stealth, it's their diversity. Solar neutrinos produced in the sun's core confirm nuclear fusion is happening right now. Supernova neutrinos, like those from 1987's famous stellar explosion, let us peer inside a dying star's heart. Even more exotic are relic neutrinos, theorized leftovers from the Big Bang's first second, so cold and slow they're nearly impossible to detect. If found, they'd be a direct line to the universe's infancy, older than the cosmic microwave background itself. Yet for all their brilliance, neutrinos hold puzzles. They oscillate, changing flavors between electron, muon, and tau types mid-flight, defying early assumptions about their mass. This quirk hints at physics beyond the standard model, perhaps even connections to dark matter. Future detectors, like the planned Dune experiment, will study neutrino beams shot through 800 miles of Earth, probing their secrets further. Every flicker of data is another stroke in a portrait of the cosmos no other particle can paint. So while light shows us the universe's face, neutrinos whisper its secrets unseen, untouchable, and utterly indispensable. They remind us that the cosmos speaks in more than one language, and if we listen closely enough, even the quietest voices can tell the grandest tales. Einstein's theory of relativity didn't just redefine gravity, it gave the universe a voice. Gravitational waves are its language, ripples in the fabric of spacetime itself, carrying tales of collisions so violent they warp reality. Picture two black holes, each weighing dozens of times more than our sun, locked in a final, lethal dance. As they spiral inward, they churn the cosmos like spoons in honey, sending out waves that stretch and compress spacetime itself. By the time those ripples reach us, they're weaker than a whisper, a distortion smaller than the width of an atom over miles of space. Yet in 2015, humanity's most sensitive instruments finally heard them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is less a telescope and more a cosmic stethoscope. Its twin detectors, separated by nearly 2,000 miles, use lasers bouncing down vacuum tubes to catch the faintest tremors in spacetime. When a gravitational wave passes, it subtly alters the laser's paths, creating an interference pattern as precise as a fingerprint. The first detection, dubbed GW150914, was the merger of two black holes over 1 billion light-years away. In less than half a second, the event released 50 times more energy than all the stars in the observable universe combined, a burst so immense it momentarily made the detector's lasers flicker like a candle in the wind. What's astonishing isn't just the detection, but what these waves reveal. Unlike light, which can be absorbed or scattered, gravitational waves slice through the cosmos unimpeded, carrying pristine information about their origins. The chirp of a black hole merges a rising frequency as the objects spiral closer lets scientists measure their masses, spins, and even the distance they traveled. Some waves arrive from epochs when the universe was half its current age, offering snapshots of a younger, wilder cosmos, and sometimes they bring surprises. In 2017, LIGO and its European counterpart Virgo spotted a collision not of black holes, but of neutron stars. A crash so bright it lit up the sky in gamma rays, X-rays, and even visible light. That single event confirmed theories about the origin of heavy elements like gold and platinum, forged in the furnace of such collisions. But the real magic lies in what we've yet to hear. Gravitational waves could carry echoes of the Big Bang itself, or hints of exotic objects like cosmic strings, theoretical flaws in spacetime left over from creation. Future observatories like the space-based LISA mission will detect lower frequency waves, potentially uncovering mergers of supermassive black holes or even the faint hum of the universe's expansion. Every ripple is a clue, a piece of a puzzle we're only beginning to assemble. The cosmos isn't just something we see, it's something we feel, vibrating through the very fabric of existence. And with each new detection, we're learning to listen. Pulsars are the universe's metronomes, ticking with a precision that puts atomic clocks to shame. Imagine a star so dense that a teaspoon of its material would weigh 1 billion tons, spinning hundreds of times per second, whipping beams of radiation through space like a cosmic lighthouse. Every rotation sends a pulse of radio waves, X-rays, or gamma rays sweeping past Earth, some as regular as a heartbeat. The first pulsar discovered in 1967 was so unnervingly rhythmic that astronomers briefly nicknamed it LGM-1, short for Little Green Men, before realizing they'd found something even stranger, a natural celestial timekeeper. What makes pulsars extraordinary isn't just their speed, but their endurance. The Crab pulsar, a remnant of a supernova observed in 1054, still spins 30 times a second, its beams flashing like clockwork despite being nearly a millennium old. These spinning corpses of massive stars are wrapped in magnetic fields trillions of times stronger than Earth's, accelerating particles to near light speeds. But here's the twist: they're slowing down ever so slightly. By measuring this spin down, astronomers can calculate a pulsar's age like counting the rings of a tree. The Vela pulsar, for instance, loses a mere 10 microseconds per year, a whisper of the universe's gradual energy drain, as if the cosmos itself is winding down. Yet pulsars aren't just cosmic curiosities, they're tools. Their impeccable timing lets scientists test Einstein's theory of relativity with brutal precision. Binary pulsars, pairs orbiting each other, emit gravitational waves, their orbits decaying exactly as predicted, a silent confirmation of spacetime's flexibility. Some, like the famed Hulse-Taylor binary, have been observed for decades, their slow in-spiral offering a front-row seat to relativity in action. Even lone pulsars serve as galactic GPS markers. By triangulating their pulses, astronomers mapped Earth's position in the Milky Way, proving we're not at the center but halfway out on a spiral arm, a speck in the grand disk. Then there are the anomalies, millisecond pulsars spun up by stealing matter from companion stars, rotate faster than blender blades, their surfaces moving at a fraction of light speed. Others, like Pulsar J1748-2446 AD, defy expectations with erratic glitches, sudden speed-ups thought to be caused by starquakes or vortices in their superfluid cores. And in 2023, astronomers found a pulsar emitting ultra-long period radio waves flashing just once every 22 minutes, a mystery that rewrites what we thought possible for these objects. Pulsars are more than dead stars, they're storytellers. Their pulses carry fingerprints of the interstellar medium, revealing clouds of gas and magnetic fields between the stars. Some beams flicker like candlelight, distorted by passing planets or asteroids. There's even the tantalizing possibility of pulsar-powered navigation for future interstellar travelers, their predictable flashes acting as beacons for ships adrift in the void. Every pulse is a timestamp, a ripple in the cosmic memory, reminding us that even in the silent dark, the universe keeps perfect time. Dark matter doesn't just hide in the shadows, it is the shadow, an invisible architect sculpting the universe from behind the curtain. We can't see it, touch it, or trap it in a lab, yet its fingerprints are everywhere. Take a spiral galaxy like our Milky Way. If stars alone dictated its rotation, the outer edges should lag behind, like children straggling at the end of a merry-go-round. Instead, stars race around the center at nearly the same speed, as if gripped by an unseen force. That's dark matter's handiwork, a gravitational glue holding galaxies together, its pull far outweighing all the visible stars, gas, and dust combined. But dark matter's influence isn't limited to single galaxies. Peering at colossal galaxy clusters, astronomers witness its grander role. When light from distant galaxies passes through these clusters, it bends, warped by the cluster's gravity, a phenomenon called gravitational lensing. Yet the distortion is too severe to be caused by visible matter alone. The only explanation, vast halos of dark matter, wrapping around clusters like invisible scaffolding, their mass bending spacetime itself. Some of these halos might even contain dark galaxies, structures so devoid of stars they're detectable only by their gravitational whispers. The real enigma isn't just what dark matter does, but what it is. Theories abound: WIMP, weakly interacting massive particles, actions, or even primordial black holes forged in the Big Bang's first moments. Whatever its form, dark matter likely dates back to the universe's infancy, a relic from when temperatures and energies were unimaginably extreme. If we could capture a single particle, it might carry secrets from that chaotic dawn, a cosmic time capsule older than atoms, older than light. That's why scientists are digging literal holes in the hunt for answers. Beneath mountains in Italy, South Dakota, and elsewhere, ultra-sensitive detectors wait in caverns shielded from cosmic rays. Some, like Xenon and Lux Zeppelin, use tanks of liquid xenon, hoping a dark matter particle will bump into a xenon nucleus and release a flash of light. Others, like the cryogenic dark matter search, chill crystals to near absolute zero, watching for the faintest vibrations. So far, the particles remain elusive, but every null result narrows the possibilities, inching us closer to a breakthrough. Perhaps the most tantalizing clue lies in the cosmos' large-scale structure. Supercomputer simulations show that without dark matter's gravitational pull, galaxies would never have clumped together as they did. The universe would be a sparse, formless void. Instead, dark matter's tendrils drew ordinary matter into its embrace, seeding the galaxies, clusters, and filaments we see today. In this way, dark matter isn't just a hidden archive, it's the quill that wrote the universe's story. And if we ever learn to read its language, we might finally understand why the cosmos looks the way it does, and what else is out there waiting in the dark. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most sophisticated filing cabinets. Picture an object plunging past the event horizon, that point of no return where gravity's grip becomes irreversible. Classical physics tells us that object is gone forever, its information shredded by the black hole's insatiable appetite. But quantum mechanics whispers a different story. The holographic principle flips the script, suggesting that every particle, every shred of data swallowed by a black hole isn't destroyed at all. Instead, it's meticulously encoded onto the event horizon's surface, like a celestial tattoo etched in Planck-scale pixels. Think of it like burning a book. To the naked eye, the pages vanish into ash, but in reality, every word, every ink molecule still exists, just transformed. Similarly, a black hole might not erase information but scramble it into a form we don't yet understand. This idea first gained traction when Stephen Hawking realized black holes emit radiation, slowly evaporating over eons. If they vanish entirely, where does the swallowed information go? The paradox sparked a decades-long debate, with some theorists suggesting the data is trapped in hidden dimensions or projected like a hologram onto the black hole's boundary. The implications are staggering. If black holes preserve information, they could be cosmic Rosetta Stones, holding records of everything they've ever consumed, an archive of galactic history written in gravity's ink. Imagine decoding the event horizon of a supermassive black hole and finding traces of ancient stars or even clues about the universe's birth. Some models suggest these data vaults operate like quantum hard drives, with bits stored in microscopic surface fluctuations. Others propose that black holes are entangled with their surroundings, creating a backup system where information is never truly lost, just redistributed. Yet the mystery deepens. If black holes do encode information, how do we retrieve it? The radiation Hawking predicted is random, like static, a far cry from the structured data that fell in. Some physicists speculate that advanced civilizations might one day crack the code, extracting knowledge from black holes like archaeologists sifting through cosmic sediment. Others argue the information is forever locked behind a firewall of quantum chaos, a cosmic keep-out sign etched into the fabric of reality. What's clear is this: black holes challenge our deepest assumptions about space, time, and information itself. They're not just gravitational monsters, they're puzzles wrapped in enigmas, testing the limits of relativity and quantum theory. And if the holographic principle holds, these dark behemoths might be the universe's ultimate librarians, silently cataloging every secret they swallow. The next time you gaze at a black hole's shadow in a telescope image, remember, you might be looking at the most sophisticated storage system in existence, a cosmic vault where the past is never truly erased, just waiting to be read. Every atom of gold in your jewelry, every fleck of uranium deep within the earth, even the calcium in your bones, these are the scattered ashes of stars that died violently long before our sun ignited. When a massive star exhausts its nuclear fuel, it doesn't fade quietly. In a final, defiant act, it collapses inward, then explodes outward with the energy of a billion suns. A supernova so bright it can outshine entire galaxies. In that cataclysm, temperatures and pressures reach unimaginable extremes, forging elements far heavier than iron, metals like gold, platinum, and uranium that ordinary stellar fusion could never produce. Then, in a cosmic exhale, the dying star hurls these newly minted elements into the void, seeding future generations of stars and planets with the ingredients for rocky worlds and life itself. Take the Crab Nebula, the ghostly remnant of a supernova witnessed by Chinese astronomers in 1054. Its swirling filaments aren't just beautiful, they're a chemical factory. Spectroscopy reveals they're rich with sulfur, oxygen, and iron elements cooked in the star's core and blasted into space. But the real treasures are the heavier elements sprinkled like cosmic dust, atoms that once belonged to a star 20 times more massive than our sun. Some of those atoms likely ended up in Earth's crust or in the device you're using right now. Your smartphone's circuitry contains gold forged in a supernova's heart, while the iodine in your thyroid was once part of a stellar explosion older than our solar system. What's astonishing isn't just the origin of these elements, but their journey. Supernova debris mixes with interstellar gas over millennia, forming dense clouds where new stars are born. Our own solar system coalesced from such a cloud 4.5 billion years ago, enriched by the deaths of countless stars. Meteorites, those ancient space rocks that occasionally land on Earth, are time capsules preserving this history. Inside them, scientists find microscopic grains of stardust, actual pre-solar particles older than the Sun, their isotopic signatures betraying their origins in different types of supernova. Some grains even carry traces of silicon carbide, a compound that could only form in the outer layers of red giants, proving our cosmic inheritance comes from more than just explosions. Yet supernova aren't the only celestial alchemists. Neutron star collisions detected through gravitational waves create staggering amounts of heavy elements in their aftermath. The kilonova event spotted in 2017 produced an estimated 10,000 Earth masses of gold and platinum in seconds, a glittering testament to the universe's creative destruction. These rare collisions might be responsible for most of the gold in the universe, meaning the ring on your finger could be relics of a neutron star's final embrace. So when you hear the phrase, "We are stardust," it's not just poetry, it's astrophysics. Every element heavier than helium in your body was forged in the heart of a dying star or the collision of stellar remnants. The oxygen you breathe, the carbon in your cells, the iron in your blood, all were scattered across space by supernova billions of years ago, only to find their way into planets, oceans, and eventually you. The universe remembers its dead not in monuments, but in atoms, weaving their legacy into the fabric of new worlds. And that means every one of us carries within us the echoes of stars that shone long before Earth existed, a living archive of the cosmos' turbulent, creative past. The silence of the cosmos isn't just eerie, it's one of the greatest mysteries in science. Enrico Fermi posed the question decades ago: if the universe is teeming with stars and planets, where is everybody? Even a single advanced civilization, given billions of years to expand, should have left some trace radio signals, megastructures, or probes drifting between the stars. Yet our telescopes hear nothing but static, and our sky shows no signs of cosmic engineers. This eerie absence is the Fermi paradox, a riddle wrapped in the universe's vast age and our own profound loneliness. But what if the signals are already here, hiding in plain sight? SETI scientists have long scanned for deliberate broadcasts, but alien messages might not come as neatly packaged radio waves. They could be encoded in pulsar timings, buried in the genetic sequences of extremophile bacteria, or even disguised as natural cosmic phenomena. Some theorists suggest advanced civilizations might use neutrinos or gravitational waves for communication, mediums far more efficient than electromagnetic waves. Imagine discovering that a pulsar's rhythmic beats aren't just natural, they are a deliberate beacon, a cosmic Morse code blinking across millennia. Then there's the darker possibility. The silence isn't an accident, but a warning. The universe could be littered with the ruins of civilizations that flared brightly and burned out. Climate collapse, nuclear war, or runaway AI might be inevitable filters that every intelligent species fails to survive. Or perhaps spacefaring cultures inevitably encounter something worse, a predatory alien intelligence that snuffs out rivals before they become threats. The Great Filter Theory suggests that life's transition to interstellar maturity is so improbable that most civilizations vanish before making contact. If true, our isolation isn't a puzzle, it's an obituary. Yet there's another twist. What if the universe forgets? Cosmic time scales dwarf human history. A civilization 1 billion years older than ours might have risen, conquered the stars, and vanished long before Earth even formed. Their artifacts could have eroded into dust, their signals redshifted into undetectable whispers. The universe doesn't preserve memories, it overwrites them. The cosmic microwave background, for all its ancient glory, is just a fading echo of the Big Bang. Given enough time, even the grandest alien empire might leave no trace behind. The Fermi paradox forces us to confront our deepest fears and hopes. Are we alone? Are we first? Or are we simply not listening the right way? Every silent night sky is a challenge, a dare to keep searching. Because if the universe has taught us anything, it's that the most extraordinary discoveries often begin with a whisper or the absence of one. Stonehenge stands silent on the English plain, its massive trilithons framing the summer solstice sunrise with eerie precision. On the other side of the world, the pyramid of Kukulkan at Chichen Itza transforms during the equinoxes, as shadows slither down its steps like a feathered serpent descending to Earth. These aren't coincidences, they're celestial blueprints, etched in stone by cultures who saw the sky not as a void, but as a sacred clock. Archaeoastronomy bridges the gap between ancient intuition and modern science, revealing how deeply our ancestors wove cosmic patterns into their daily lives. Consider Newgrange, a 5,000-year-old Irish tomb older than the pyramids. Its narrow passage aligns perfectly with the winter solstice sunrise, flooding the inner chamber with golden light for just 17 minutes each year. Modern astronomers calculate this alignment couldn't have been accidental. It required generations of precise observation. But was it merely a calendar or something transcendent? The tomb's builders left no written records, but their stones whisper of a belief that the sun's rebirth mirrored cycles of life, death, and renewal. The Maya took celestial precision even further. Their Dresden Codex contains tables predicting Venus's movements centuries in advance, accurate to within hours. At El Caracol, a spiral observatory in Chichen Itza, narrow windows frame Venus's extreme positions in the sky, tracking its 8-year cycle. For the Maya, Venus wasn't just a planet, it was Kukulkan, a deity whose movements dictated when to wage war or plant crops. This fusion of myth and mathematics hints at a world view where the cosmos was alive, its rhythms inseparable from human fate. Meanwhile, in the American Southwest, the Chacones carved spiral petroglyphs that transform into daggers of light during solstices and equinoxes. At Machu Picchu, the Intihuatana stone serves as a solar clock, its shadows marking sacred dates. These cultures, separated by oceans and millennia, shared an obsession, timekeeping tied not to gears or digits, but to the dance of celestial bodies. What fascinates modern researchers isn't just the accuracy of these ancient observatories, but their purpose. Were they practical tools for agriculture or portals to the divine? The answer might be both. In societies where survival depended on reading seasons, the sky was a farmer's almanac. But its predictability also suggested order beyond human chaos, a cosmic script written by gods or ancestors. Today, as our satellites map exoplanets and probe dark matter, we're still chasing that same longing to find meaning in the stars' silent language. The stones remain, aligned to heavens their builders could never fully understand, yet somehow knew better than we ever will. The night sky has always been humanity's first storybook, its pages filled with heroes, monsters, and gods sketched in starlight. Long before telescopes or star charts, ancient cultures connected the dots between bright stars, seeing not random scatterings but epic tales written overhead. The zodiac, those 12 constellations along the sun's yearly path, is more than an astrological gimmick. It's a celestial archive, a way for civilizations from Babylon to Mesoamerica to encode their understanding of time, seasons, and even cosmic disasters. Take Orion, the hunter striding across winter skies. To the Greeks, he was a boastful giant slain by Artemis. But dig deeper, and you'll find echoes of this story everywhere. The ancient Egyptians saw Osiris, god of rebirth, in those same stars, his belt aligning with the Nile's annual floods. Half a world away, the Maori recognized Tortaru, an ancestor guiding fishermen. These aren't just coincidences, they're evidence of a universal human impulse to turn the cosmos into narrative. The stars stayed the same, but the stories adapted, each culture projecting its fears, hopes, and wisdom onto the glittering canvas above. What's fascinating is how much practical astronomy hides in these myths. The zodiac's division into 12 signs mirrors the moon's 12.4 cycles each year, a tidy way to track time. The Age of Aquarius isn't just a hippie slogan. It reflects the slow wobble of Earth's axis called precession, which shifts the sun's equinox position against the stars over 26,000 years. Babylonian astronomers noted this drift millennia ago, encoding it in their star lore. Even the Greek myth of Phaethon, who lost control of the sun chariot and scorched the Earth, might describe a real comet or meteor storm witnessed in prehistory. But the zodiac's genius lies in its duality. It was both almanac and allegory, helping farmers plant crops while also explaining life's mysteries. In China, the 28 lunar mansions tracked the moon's path, but also symbolized celestial bureaucrats governing human affairs. The Maya tied their zodiac to sacred animals, using it to predict eclipses and royal destinies alike. These systems weren't primitive, they were sophisticated memory technologies, blending observation with tradition to preserve knowledge across generations. Today, we've swapped star myths for star catalogs, yet the zodiac's legacy endures. Every time you glance at your horoscope, even skeptically, you're touching a tradition stretching back to Babylon's clay tablets. The stars haven't changed, but our relationship with them has. Where ancients saw dragons and archers, we see neutron stars and exoplanets, yet both perspectives share the same awe, the same hunger to find meaning in the dark. The next time you spot Scorpius's curved tail or Leo's sickle-shaped mane, remember, you're not just seeing constellations, you're reading the oldest book in existence, one whose authors spanned continents and centuries, all united by the stories they saw burning in the night. Stories of world-ending catastrophes echo through every ancient culture. Babylonian tablets speak of gods flooding the earth. Hindu texts describe celestial fire, while Aboriginal Dreamtime stories tell of a time when the sky fell. These aren't just imaginative myths, they could be humanity's oldest history books written in the language of trauma. Take the Great Flood narratives found in over 200 cultures worldwide. Modern geologists point to a real candidate, the Black Sea deluge around 5,600 BCE, when rising Mediterranean waters breached a natural dam, submerging an area the size of Ireland in months. For coastal societies, this wasn't just a bad storm, it was the apocalypse, an event so traumatic it seared into collective memory for millennia. But water wasn't the only threat from above. The Mahabharata's vivid account of a blazing column of smoke brighter than 1,000 suns could describe an asteroid impact, while Native American oral traditions mention a sky serpent, a meteor, bringing fire and quakes. In 2019, researchers found a 31-kilometer-wide crater beneath Greenland's ice, likely formed by a mile-wide iron asteroid just 12,000 years ago, around the time the Clovis people vanished from North America. Their disappearance coincides with the Younger Dryas period, a sudden return to Ice Age conditions that may have been triggered by cosmic bombardment. Ancient stories of long winters, like the Norse Fimbulwinter or the Greek myth of Demeter's grief, could be distant memories of this global chill. Supernova leave scars too. Around 3200 BC, a dying star may have exploded just 600 light-years away, bathing Earth in enough radiation to leave traces in tree rings worldwide. Chinese records from 1054 CE detail a guest star bright enough to cast shadows for weeks, now identified as the Crab Nebula's birth. Could such an event have terrified our ancestors? Aboriginal tales from Australia describe a time when two suns crossed the sky, possibly a supernova visible even by day. Even more intriguing is the Vela supernova remnant, which lit up the southern sky around 12,000 years ago. At that time, early human artists in places like Göbekli Tepe were carving peculiar symbols, including a scorpion and a vulture, that some researchers argue mirror constellations near Vela's location. Coincidence or celestial cartography? The most chilling possibility involves gamma-ray bursts, cosmic death rays capable of sterilizing planets. A nearby burst around 40,000 years ago might explain the sudden disappearance of Australia's megafauna and the near extinction of early humans. Indigenous stories of skyfire causing mass animal deaths take on new weight when paired with evidence of radiation spikes in ice cores. Scientists even speculate that a burst could have triggered the legend of Phaethon, the Greek youth who crashed the sun chariot, scorching Africa into desert. What's striking isn't just the accuracy of these ancient accounts, but their resilience. Without writing, early societies encoded warnings in myth, passing down survival lessons across generations. The Klamath people's tale of Mount Mazama's eruption 7,700 years ago preserved verbatim, until geologists confirmed it matched the volcanic timeline, proves oral traditions can outlast stone. Today, as we scan the skies for potential threats, we're not so different from those ancestral storytellers. The difference, they didn't have telescopes, just the searing clarity of lived experience, burned into legend. Their voices, carried across centuries, remind us that the universe isn't just a spectacle. Sometimes it's a sniper. The golden records aboard Voyager 1 and Voyager 2 aren't just artifacts, they're bottles cast into the cosmic ocean, carrying whispers of a civilization that once looked up and dreamed of connection. Etched onto 12-inch gold-plated copper discs, these time capsules contain 115 images, greetings in 55 languages, and 90 minutes of Earth's greatest hits, from Bach's Brandenburg Concerto to Chuck Berry's Johnny B. Good, but what's most striking isn't the content, it's the audacity behind it. In 1977, as the probes launched, humanity knew these records might outlast not just our species but our star. They're less about who might find them and more about the act of reaching out, a defiant gesture against the universe's indifference. Consider the challenge the team faced. How do you introduce Earth to an intelligence with no shared language, history, or senses? Carl Sagan and his collaborators turned to mathematics and physics, embedding a pulsar map on the record's cover. The etching points to our sun's location using 14 pulsars, cosmic lighthouses whose regular beats could guide a future traveler home. Even the record's playback instructions are a universal language, a stylus tucked into the casing, with diagrams showing how to spin the disk at 16 2/3 revolutions per minute. The assumption, any civilization advanced enough to intercept Voyager would recognize binary code and hydrogen's hyperfine transition, the most basic elements of science. Yet the records reveal as much about our hopes as our knowledge. The sounds a baby's cry, waves crashing, a heartbeat are fragments of a planet teeming with life and impermanence. The images from a supermarket to a Tibetan lamasery capture both our mundane routines and our highest aspirations. There's humor here too. The team included a NASA engineer's brainwaves converted to audio, a love letter etched in neurons. But the most haunting selection might be the greeting from UN Secretary General Kurt Waldheim. We step out of our solar system into the universe seeking only peace and friendship. A noble sentiment launched during the Cold War's peak tensions. Voyager's golden records are now the farthest traveling human-made objects, drifting beyond the heliosphere into interstellar space. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star in Camelopardalis. By then, if humanity still exists, we may have spread to the stars or vanished without a trace. Either way, these disks will remain, their gold surfaces barely tarnished by cosmic rays, carrying snapshots of a species that once wondered if it was alone. They're not just messages to aliens, they're mirrors showing us at our most vulnerable and brave. A reminder that memory isn't just about the past, it's a bridge to futures we'll never see. Quantum entanglement isn't just physics' strangest party trick, it might be the universe's ultimate filing system. Picture two electrons born from the same atomic event, their spins forever linked even if separated by galaxies. Change one spin and its partner instantly flips too, as if space and time don't exist between them. This spooky action at a distance, as Einstein called it, defies classical logic. But what if this bizarre connection isn't just a momentary link? Emerging theories propose that entangled particles don't just communicate, they remember, preserving traces of their shared history like quantum fingerprints that never fade. Take the work of physicists exploring quantum Darwinism. When particles interact with their environment, certain quantum states get copied and reinforced across multiple systems like whispers spreading through a crowd until they become common knowledge. This process could create a natural selection for quantum information, where only the most stable states survive decoherence. The result? A passive recording mechanism where the universe itself chooses which quantum memories to preserve. It's as if every photon collision, every atomic bond leaves faint etchings in the fabric of reality, detectable if you know how to look. The implications rewrite how we view cosmic memory. Traditional data storage, whether DNA or hard drives, degrades over time. But quantum information encoded in entanglement might persist indefinitely, immune to the ravages of heat or radiation. Experiments with nitrogen vacancy centers in diamonds already show how quantum states can be stored for hours at room temperature. Scale this up to cosmological levels, and you're looking at a universe where every particle interaction from the Big Bang's first moments to last night's supernova could leave quantum breadcrumbs behind. Some theorists even speculate that dark matter's elusive nature might stem from it being a vast, cold storage medium for quantum information we can't yet access. Then there's the holographic principle's radical suggestion that all quantum information falling into a black hole gets imprinted on its event horizon. If true, black holes aren't just destroyers, they're cosmic librarians, compressing data onto a two-dimensional surface like a celestial DVD. Extend this idea, and the entire universe might function similarly, with every event encoded in Planck-scale pixels at the boundary of spacetime. We're not just living in a universe with memory, we might be living inside one. The boldest idea comes from quantum retrocausality. Certain interpretations suggest that future quantum measurements can influence past particle states, as if causality itself has a feedback loop. Imagine digging through quantum archives only to find entries that haven't been written yet. It sounds like science fiction, but delayed choice experiments show particles behaving as if they know what measurement will be made of them later. This twists cosmic memory into something even stranger, a ledger where the past and future are still negotiating the terms. Whether any of these theories hold up, one thing's clear: the universe forgets nothing lightly. From entangled particles whispering across light years to black holes encoding fallen stardust, reality seems hardwired to preserve its story. We're just beginning to learn the language, and the library might be infinite. Imagine Earth not as a rock hurtling through space, but as a cosmic storyteller, its very soil, oceans, and atmosphere turning the pages of a living diary written over 4.5 billion years. This is the heart of the Gaia Hypothesis, the revolutionary idea that our planet functions like a self-regulating superorganism. James Lovelock's theory didn't just redefine Earth, it gave our world a voice, suggesting that every layer of sediment, every fluctuation in oxygen levels, and even the dance between predators and prey are entries in an epic planetary memoir. Take the Great Oxidation Event, a chapter written 2.5 billion years ago when cyanobacteria flooded the atmosphere with oxygen. That wasn't just a chemical accident, it was Earth's first climate intervention, a microbial revolution that permanently altered the planet's trajectory. The rust-colored bands in ancient rock formations, those are the ink, iron oxides precipitated out of seawater when oxygen first met the oceans. Fast forward to the Cretaceous period, and Earth's diary bears another dramatic entry, the Chicxulub impact. Iridium-rich clay layers mark the asteroid that wiped out the dinosaurs, but also reveal how quickly life rebounded, with ferns and fungi dominating within decades. These aren't random events, they're proof of a system constantly adjusting, rebalancing, remembering. What's astonishing is how precise this record-keeping is. Ice cores from Antarctica contain bubbles of ancient atmosphere, snapshots of CO2 levels stretching back 800,000 years. Tree rings tell tales of volcanic winters and solar cycles. Even the shells of long-dead plankton sinking to the seafloor carry isotopic signatures of past temperatures. Together, they form a planetary archive so detailed it puts human history books to shame. The Amazon rainforest, for instance, isn't just a carbon sink, it's a climate control system, exhaling moisture that seeds clouds and regulates temperatures across continents. Lovelock argued this isn't coincidence, it's collaboration on a planetary scale, but Gaia's diary has warnings too. The same layers that show Earth's resilience also reveal its fragility. The Permian-Triassic extinction, dubbed the Great Dying, left scars in sulfur-rich rocks, evidence of runaway greenhouse gases and acidifying oceans. Today, as we burn fossil fuels, we're adding pages to that story at a pace unmatched in geological time. The difference: this extinction event would bear a new signature: microplastics in sediment, radioactive isotopes from nuclear tests, and the sudden spike in carbon isotopes from industrialization, all markers of a species that became a geological force. If alien scientists ever cracked Earth's diary, what would they conclude? Perhaps they'd see a planet that survived asteroid impacts and ice ages, only to face a novel threat: intelligence that forgot its place in the system. Or maybe they'd find hope in the last chapters: the ozone layer healing after we banned CFCs, or wetlands regenerating when given space. Gaia doesn't judge, she records. And her most profound lesson might be this: life isn't just riding Earth cycles, it's writing them one organism, one epoch, one choice at a time. Every story has an ending, and the universe's final chapter might be the quietest of all, a slow fade into darkness where even memory itself dissolves. This is the heat-death scenario, a fate dictated by entropy, the relentless force that drives all systems toward disorder. Picture a cup of hot coffee left on the counter. Over time, its heat spreads out, blending with the air until it's gone. Now scale that up to cosmic proportions. Stars burn out, black holes evaporate, and eventually, the universe becomes a vast, lukewarm sea of particles so thinly spread that no new structures can form. No galaxies, no planets, not even atoms, just a faint, uniform whisper of energy too weak to power even a single thought. But here's the chilling twist. In this frozen twilight, information itself could vanish. Black holes, those cosmic vaults we once thought preserved data, might eventually decay into radiation, erasing the records they swallowed. Even quantum entanglement, the universe's most stubborn glue, could fray as particles lose their connections across unimaginable distances. It's as if the cosmos, after billions of years of meticulously cataloging every event, finally loses its grip on the ledger. The heat death isn't just an end, it's the ultimate forgetting. Yet some theories push back against this bleak finale. Quantum mechanics hints that information can never truly be destroyed, only scrambled beyond recognition. Like a book burned to ash, the words might still exist in some form, just unreadable. Could the universe, in its final moments, still cling to its history in ways we can't yet fathom? Gravitational waves, those ripples in space-time, might persist even in the void, carrying faint echoes of long-dead collisions. And if the holographic principle holds, perhaps the universe's entire history remains encoded on some distant boundary, a cosmic epitaph etched into the fabric of reality itself. The deeper question isn't just whether the universe remembers, but what it means to forget. If every trace of our existence, every artifact, every signal, even the atoms in our bones disperses into nothingness, does it matter that we were ever here? The heat death forces us to confront the fragility of meaning in an indifferent cosmos, but it also sharpens the urgency of now. Every discovery we make, every story we preserve, is a defiance of that eventual silence. We may not outlast the universe, but for this fleeting moment we're its scribes, its witnesses, turning the chaos of existence into something worth remembering. Astrobiology's most tantalizing idea isn't just about finding life. It's about tracing our own cosmic ancestry. Panspermia, the theory that life's building blocks or even dormant microbes rode to Earth on comets or asteroids, transforms the search for extraterrestrial life into something profoundly personal. If true, the organic molecules in your cells might not be purely terrestrial. They could be interstellar hitchhikers, forged in the icy depths of a molecular cloud billions of years before our solar system formed. The evidence isn't science fiction. Meteorites like Murchison, which fell in Australia in 1969, contain amino acids, the same ones that form proteins in your body. Even more startling, some of these space rocks carry nucleobases like uracil, a key component of RNA. These aren't just random chemicals, they're the raw materials of life, delivered to a young Earth like cosmic care packages. This raises a staggering possibility. Life might not have originated here. Instead, Earth could have been a fertile landing pad for seeds already scattered across the galaxy. Imagine a scenario where extremophile bacteria, encased in protective ice, survived eons in the vacuum of space before splashing into Earth's primordial oceans. It sounds fantastical, but consider Deinococcus radiodurans, a real-world microbe that shrugs off radiation doses lethal to most organisms. Dubbed Conan the Bacterium, it can survive years of desiccation and cosmic rays, proof that life, once started, is stubbornly adaptable. If such microbes exist on icy moons like Europa or Enceladus, could they have made the journey here, riding debris ejected by asteroid impacts? That's why missions like NASA's A Mars Sample Return or the upcoming Europa Clipper aren't just hunting for alien life, they're digging for our own family tree. Mars, once warmer and wetter, might have hosted life before Earth did. if future rovers find fossilized microbes in Jezero crater's ancient lakebed, their genetic blueprint, if preserved, could reveal whether they're cousins or complete strangers to Earth life. Even more compelling, Europa's subsurface ocean, kept liquid by tidal forces, could harbor ecosystems fed by hydrothermal vents similar to those that nurture life in Earth's deepest trenches. A single cell found there with biochemistry mirroring ours would hint at a shared lineage stretching back to a common ancestor that traveled between worlds. But panspermia isn't the only plot twist in this cosmic detective story. Alternative theories suggest life's precursors might have formed in the protoplanetary disk itself, cooked in the warmth of young stars. The real answer could lie in a combination, a cosmic relay where each step, from interstellar clouds to asteroid impacts, played a role in assembling life's puzzle. Either way, the implications are humbling. If life jumps between planets as easily as spores drift on the wind, then the universe might be less a barren wasteland and more a sprawling network of interconnected biospheres. The next time you gaze at the stars, consider this. You might not just be looking for life out there. You might be looking for home. Every atom in your body, every strand of DNA, could be part of an epic migration story written in the chemistry of comets and the geology of distant moons. And if future missions find even a single microbe with a shared genetic heritage, it won't just answer whether we're alone, it will tell us we've always belonged to something far greater. On a quiet August night in 1977, a telescope in Ohio caught something impossible to ignore, a burst of radio waves so intense it dwarfed the background noise of the cosmos. For 72 seconds, the Big Ear radio telescope locked onto a signal coming from the direction of the constellation Sagittarius, pulsing at exactly the frequency scientists had long predicted an alien civilization might use, 1420 MHz, a quiet channel where hydrogen, the universe's most abundant element, naturally resonates. The signal's intensity spiked and faded in a perfect curve, matching what you'd expect if it came from a distant, focused source passing through the telescope's field of view. When astronomer Jerry Amon saw the data printout days later, he circled the alphanumeric sequence in red pen and scribbled a single word in the margin: "Wow." What made the WOW signal extraordinary wasn't just its strength, 30 times louder than cosmic static, but its specificity. It occupied a narrow sliver of bandwidth, as if someone had tuned a cosmic radio to a precise station. Natural phenomena like comets or pulsars usually broadcast across a range of frequencies, but this was surgically precise, almost engineered. The kicker: despite decades of follow-up scans, including modern projects like the SETI Institute's Allen Telescope Array, the signal never repeated. It was a cosmic one-hit wonder, leaving astronomers with a maddening question: was this a fleeting hello from another civilization, or just a bizarre celestial fluke? Theories abound. Some suggest it could have been a reflected human signal, maybe a satellite or military transmission bouncing off space debris. But calculations show earthly interference would have left different fingerprints in the data. Others propose a natural origin, like a hydrogen cloud excited by an unknown cosmic event. Yet nothing in our current catalogues of astrophysical phenomena quite matches the WOW signal's profile. Then there's the tantalizing, if controversial, possibility. What if it was artificial? If so, it wouldn't be a continuous beacon, but more like a lighthouse beam sweeping past Earth, meaning we might have intercepted just a fragment of a repeating transmission that takes years or even centuries to cycle back our way. The signal's enduring mystery highlights a deeper truth about the search for extraterrestrial intelligence. Space is vast and time is vaster still. A civilization could beam signals for millennia, and we might catch only a whisper if our telescopes aren't pointed in the right direction at the right moment. The WOW signal could have been a cosmic ping, a test message, or even the remnants of a long-dead civilization's final broadcast, its senders long gone by the time their signal reached us. What's equally fascinating is how the WOW signal reshaped SETI approach. Before 1977, the search for alien signals was seen as fringe science by many. But the WOW signal's sheer anomaly forced even skeptics to admit, there are things out there we don't understand. Modern SETI projects now deploy banks of telescopes scanning millions of frequencies simultaneously, armed with algorithms to flag anomalies in real time. Yet despite all this tech, the WOW signal remains in a class of its own, a siren song from the void that refuses to be explained away. Perhaps the signal's greatest gift is its ambiguity. In a universe that often feels indifferent, it's a reminder that some mysteries still spark that childlike wonder, the urge to scribble, "Wow," in the margins of history. Whether it was a greeting, a glitch, or something beyond our current physics, it challenges us to keep listening, to stay curious, because somewhere in the cosmic static, there might be another signal waiting. And next time, we might just be ready to answer. KIC 8462852, better known as Tabby's star, doesn't behave like any other sun in the galaxy. Nestled in the constellation Cygnus, this seemingly ordinary star first made headlines in 2015 when astronomers noticed its light dipping erratically, sometimes by as much as 22%. Stars dim for plenty of reasons: planets passing in front, dust clouds drifting by, but Tabby's star's fluctuations were chaotic, asymmetric, and utterly unpredictable. No natural phenomenon in our playbook could fully explain it. That's when the whispers began. What if we were seeing something artificial? The most tantalizing and controversial theory suggested a Dyson swarm, a vast network of solar collectors built by an advanced civilization to harness their star's energy. For a brief, electrifying moment, humanity wondered if we'd stumbled onto the ultimate cosmic message. We are here. Of course, extraordinary claims demand extraordinary evidence. Further study pointed to less sensational explanations: swarms of comets, uneven dust clouds, or even the remnants of a devoured planet could account for the star's odd flickering. Yet the real legacy of Tabby's star isn't about proving or debunking alien megastructures. It's about how anomalies, even false alarms, sharpen our ability to listen to the universe. Before this star's bizarre behavior, no one had systematically combed through decades of telescope data for similar anomalies. Now, thanks to the frenzy it sparked, astronomers have launched projects like the Galileo Initiative, scanning millions of stars for irregular dimming patterns. Tabby's star taught us to expect the unexpected, to question whether natural is just a placeholder for not yet understood. What's equally fascinating is how this star mirrors humanity's own evolving relationship with cosmic memory. Centuries ago, a flickering star might have been interpreted as an omen or a god's whim. Today, we pass its light curves with algorithms, searching for signatures of intelligence. Both approaches share a common thread: the conviction that the cosmos is speaking if only we learn its language. Tabby's star's greatest gift might be its ambiguity, a reminder that the universe's memory isn't just stored in light or gravity waves, but in the questions we're brave enough to ask. Consider the broader pattern. From the WOW signal to fast radio bursts, cosmic mysteries follow a familiar rhythm: discovery, speculation, and more often than not, a mundane explanation. Yet each time the process leaves science richer, with new tools and finer-tuned questions. The search for alien megastructures led to breakthroughs in detecting exocomets and circumstellar debris. In that sense, Tabby's star isn't a dead end, it's a detour that expanded the map. The next time you look up at Cygnus, remember, Tabby's star still flickers, still keeps its secrets. Whether its story involves alien engineers or never-before-seen astrophysics, it's already done its job. It's shaken us out of complacency, proving that the universe's memory isn't just about the past. Sometimes it's about the future, the discoveries we haven't made yet, the voices we're only beginning to hear, and that's the most thrilling mystery of all. The multiverse theory doesn't just expand our notion of reality, it shatters it, suggesting the cosmos might be less a single story and more an infinite library, each universe a volume with its own set of physical laws. Imagine flipping through these books, one where gravity is stronger, making stars burn out in a cosmic blink, another where light moves sluggishly, stretching seconds into centuries. Some universes could mirror ours almost exactly, differing only in the slightest details, a world where you turned left instead of right one morning, altering the course of history. Others might be so alien that time flows backward, or matter never clumped into galaxies at all. This isn't science fiction. It's a serious framework debated by physicists, rooted in quantum mechanics, string theory, and cosmic inflation. Think of cosmic memory in this context. If the multiverse is real, then every event that could happen does happen somewhere. The Big Bang wasn't a one-time explosion, but a never-ending cascade of creation, each bubble universe carrying its own unique imprint of that primordial moment. In one universe, the cosmic microwave background might show faint scars from collisions with other universes. In another, dark energy's strength could be so weak that galaxies never formed, leaving behind a vast, empty darkness. The implications are staggering. Our universe's history isn't the history, just one thread in an unimaginably vast tapestry. This idea challenges how we define memory itself. Traditionally, we think of memory as linear, a sequence of cause and effect preserved in light, matter, or gravitational waves. But in a multiverse, memory becomes fractal. A black hole's evaporation in one universe might leave echoes in another through quantum entanglement, like ripples crossing between ponds. The laws of physics themselves could be relics of deeper, meta-cosmic processes, shaped by conditions we'll never observe directly. Some theories even propose that universes remember their ancestors, inheriting subtle traits through cosmic natural selection, a Darwinism operating on the scale of existence itself. The wildest possibility, we might already have evidence of the multiverse. Anomalies in the cosmic microwave background, like the mysterious cold spot, could be bruises from collisions with other universes. Quantum experiments showing particles existing in multiple states until observed might hint at parallel realities bleeding into ours. Even the sheer improbability of our universe's finely tuned constant gravity, just strong enough to form stars, but weak enough not to crush atoms, makes more sense if infinite variations exist. Yet the multiverse isn't just a scientific hypothesis. It's a philosophical mirror forcing us to confront our place in the grand scheme. If every possible version of reality exists, does our choices' meaning dissolve or expand? The answer might lie in how we reframe the question. Instead of a single cosmic memory, we're part of an infinite archive, each universe a sentence in a story too vast to read. And that's the most humbling thought of all. Somewhere out there, another version of you is pondering this very idea, staring at the same stars, wondering if they're looking back. Simulation hypothesis. Are we the data? If our universe is a simulation, its memory resides in the code of a higher dimensional computer. Glitches, mathematical constants, or quantum uncertainties might be artifacts of this programming. While speculative, the hypothesis forces us to ask, could the universe's memory be someone else's storage system? And if so, who's the programmer? Picture the universe as an unfathomably advanced video game. It's every galaxy, particle, and law of physics rendered in perfect detail by lines of code. In this scenario, cosmic memory isn't etched in starlight or gravitational waves. It's stored in bits and bytes, a celestial hard drive maintained by intelligences we can't begin to comprehend. The idea isn't as far-fetched as it sounds. Right now, humanity creates simulations of everything from weather patterns to protein folding. If our rudimentary models can predict hurricanes or design drugs, what might a civilization a billion years more advanced achieve? Their simulations could be so flawless, their virtual inhabitants, us, might never suspect they're living in a constructed reality. This is the heart of the simulation hypothesis, a theory that gained traction when philosopher Nick Bostrom calculated the staggering odds. If even one civilization ever reaches the technological capacity to run ancestor simulations, the number of artificial universes would dwarf the single, real one, making it statistically likely we're in one. The clues proponents argue are hiding in plain sight. Take quantum mechanics, where particles exist in blurred states until observed, a quirk that feels suspiciously like a rendering optimization, saving processing power by only calculating definite properties when needed. Or the universal speed limit of light, which could be a built-in frame rate preventing the simulation from overloading. Even mathematical constants like pi or the fine structure constant might not be fundamental truths, but carefully chosen parameters to keep the code stable. Then there are the glitches. Astronomers have spotted anomalies like galaxies spinning too fast for their visible mass, or particles behaving unpredictably in double-slit experiments. Could these be bugs in the cosmic software, patches waiting to be applied? Some theorists point to déjà vu or Mandela effects, moments where collective memory contradicts recorded history, as potential system errors. Others speculate that black holes aren't just space-time singularities, but data compression nodes, swallowing information to free up storage in an overburdened simulation. But if we're living in someone else's program, who's running it? The candidates range from post-human descendants recreating their ancestors, us, for study, to alien civilizations treating universes like lab experiments. There's even the chilling possibility we're entertainment, a cosmic reality show for beings whose motives we can't fathom. Or perhaps the simulation isn't conscious at all, but an automated process humming in the background of a higher dimensional universe, its creators long gone. The simulation hypothesis does more than question reality. It reframes cosmic memory itself. If the universe is code, then every supernova, every dinosaur bone, every thought you've ever had is data in an archive beyond spacetime. Our search for meaning shifts from "why are we here" to "what's our purpose in the program?" Are we NPCs in a grand strategy game, or self-aware AI pushing against our boundaries? The answer might lie in hacking the system. Some scientists have proposed experiments to test the hypothesis, like hunting for pixelation in the fabric of reality, or exploiting computational limits to trigger detectable rounding errors. Others suggest that if we ever develop our own perfect simulations, it would be near proof we're in one too, a hall of mirrors stretching to infinity. Whether the simulation hypothesis is profound truth or philosophical sleight of hand, its power lies in the questions it forces us to confront. If the cosmos is a simulation, then every law of physics is a line of code, every black hole a recycle bin, and every human mind a subroutine in a program vaster than comprehension. And if that's true, the most haunting thought isn't that we're artificial, it's that somewhere, someone might one day hit delete. Time's arrow points relentlessly forward, etching the universe's history into the fabric of reality. Yet the deeper we probe, the more this simple story unravels. At first glance, the concept seems straightforward. Entropy, the measure of disorder in a system, always increases over time. A shattered glass doesn't reassemble itself. Smoke disperses but never retreats back into the chimney. This irreversibility is why we remember the past but not the future. The universe, in this view, is like a meticulous archivist, preserving every collision, every chemical reaction, every star's death in the ledger of increasing entropy. But dig beneath the surface and contradictions emerge. Quantum mechanics paints a stranger picture. When two particles become entangled, their fates intertwine in ways that defy classical notions of time and space. Measure one particle's spin here on Earth, and its partner instantaneously knows its state, whether it's across the room or on the other side of the galaxy. This connection isn't just faster than light, it's timeless, as if the particles share a memory untouched by the flow of entropy. Einstein called it spooky action at a distance, but it's more like spooky recall, a cosmic memory that operates outside the arrow of time we're bound by. The tension between these two worlds, the orderly march of entropy and the tangled web of quantum memory, is one of physics' greatest unsolved puzzles. Some theorists suggest the answer lies in scale. At the macroscopic level, where trillions of particles interact, entropy's grip is ironclad. Yet at the quantum level, particles dance to a different rhythm, their memories preserved in entanglement's delicate threads. Others propose that time's arrow isn't fundamental at all, but an emergent property like temperature arising from the motion of atoms. In this view, the universe might remember the past simply because that's the direction in which complexity grows, not because time itself has a preferred flow. Then there's the wild card, black holes. These cosmic paradox machines seemingly destroy information, violating quantum mechanics' insistence that memory must be preserved. Yet the holographic principle suggests that every bit of data swallowed by a black hole is encoded on its event horizon, like a celestial backup drive. If true, black holes might be the ultimate arbiters of cosmic memory, enforcing entropy's rules while preserving quantum connections in ways we don't yet understand. What's clear is this: the universe's memory isn't a single, monolithic record. It's a patchwork of competing systems, some linear, some looping, some defying time altogether. The coffee cup that shatters and never reassembles, the entangled particles whispering across light years, the black holes rewriting the rules, they're all part of the same story. And somewhere in the tension between them lies the secret of why time flows forward at all, and whether, in some corner of the cosmos, it might even flow backward. Until we solve that riddle, the universe's memory remains a fractured mirror, reflecting back at us in ways we're only beginning to comprehend. Imagine composing a letter you know won't be read for centuries, or perhaps ever. That's the essence of METI, messaging extraterrestrial intelligence, humanity's deliberate attempt to carve our presence into the universe's memory. Unlike passive SETI programs that listen for alien signals, METI actively broadcasts, beaming carefully crafted messages toward nearby star systems with powerful radio telescopes. The 1974 Arecibo message, aimed at the Hercules globular cluster 25,000 light-years away, was our first cosmic postcard, encoding everything from DNA's structure to our solar system's layout in binary pulses. Since then, projects like A Simple Response in 2016 have transmitted crowdsourced thoughts toward Polaris, while the Sonar Calling Initiative blasted electronic music at JJ273, a red dwarf just 12 light-years away. Each transmission is a time capsule, a deliberate scratch on the universe's surface saying, "We were here, but not everyone agrees we should be signing the guest book. Prominent critics like Stephen Hawking warned that announcing our presence could be catastrophically naive, comparable to Native Americans welcoming Columbus, with similarly grim outcomes. The darker scenarios are chilling: a resource-hungry civilization intercepting our signals, tracing them back to Earth, and viewing our planet as ripe for conquest. Even if aliens aren't overtly hostile, their mere response could destabilize human society. A confirmed message might trigger panic, religious crises, or geopolitical scrambles to control the narrative. METI proponents counter that any civilization advanced enough to detect and decode our faint signals would likely have moved beyond aggression, their survival dependent on cooperation rather than conquest. But can we afford to gamble on that assumption? The debate exposes a deeper tension about legacy. Are we the reckless newcomers shouting into the dark, or the responsible custodians preserving Earth's silence? Ancient cultures left cave paintings and pyramids to declare, "We mattered." METI offers a modern equivalent, a way to ensure humanity isn't forgotten, even if we vanish tomorrow. Yet there's irony in our urgency. The stars we're targeting are so distant that any reply would take lifetimes to arrive. Our messages are less about conversation and more about carving our initials into the cosmic tree, a testament that once, against all odds, a species on a pale blue dot dared to reach out. Perhaps the most profound question isn't whether we should message, but what we say. Early transmissions leaned on mathematics and physics, the universe's supposed common language. But newer efforts embrace art and culture, like the Beyond Project's inclusion of music and AI-generated poetry. If aliens decode these, they won't just learn our atomic numbers, they'll glimpse our creativity, our loneliness, our hunger to connect. That shift reflects a growing realization. Cosmic memory isn't just about preserving facts but meaning. 1,000 years from now, our radio waves may be all that's left of us, drifting through space like echoes in an empty cathedral. So while scientists argue over protocols and politicians fret over risks, the rest of us are left with a haunting thought. Every tweet, every broadcast, every accidental radar pulse leaking into space is already part of our cosmic footprint. The universe remembers everything. The only choice is whether we shape that memory or let the void write our epitaph for us. The James Webb Space Telescope isn't just a machine, it's a time machine. Perched 1,000,000 miles from Earth, its gold-plated mirrors catch whispers of light that have traveled for over 13 billion years, carrying snapshots of the universe's infancy. Unlike Hubble, which sees mostly visible light, JWST infrared vision pierces through cosmic dust like an X-ray, revealing the hidden architecture of star-forming nebulae and the faint glow of galaxies so ancient they shouldn't exist. Take its jaw-dropping image of galaxy cluster SMACS 0723. What looks like a splash of glitter is actually a gravitational lens, warping space-time so severely that it magnifies galaxies from the universe's toddler years, some as young as 300 million years after the Big Bang. These aren't just pretty pictures, they're crime scene photos from the dawn of creation. What's rewriting textbooks is how developed these early galaxies appear. Conventional wisdom said the first galaxies should be small, chaotic blobs. Instead, JWST found fully formed spirals and disks, their stars already heavy with metals elements that theoretically needed multiple stellar generations to forge. It's like digging up a smartphone in a medieval castle. The universe's growth spurt might have been far faster than we imagined. Then there's the mystery of JWST 14, a galaxy so bright and massive in the early cosmos that it defies current models of dark matter's role in galaxy formation. If confirmed, it could mean our understanding of cosmic evolution is missing entire chapters. But JWST archaeology isn't limited to the distant past. Its spectrographs act as cosmic chemists, sniffing out the molecular makeup of exoplanet atmospheres. When it analyzed WSP-96b, a gas giant 900 light-years away, the data revealed water vapor, clouds, and even hints of haze, ingredients common in our solar system, yet arranged in alien configurations. The real jackpot, K218b, a Hycean world where JWST detected dimethyl sulfide, a compound on Earth produced only by living organisms. Before you book your ticket, though, false positives are possible. Volcanic activity or unknown chemistry could mimic biosignatures. That's why JWST next targets include TRAPPIST-1e, a rocky planet in its star's habitable zone where it'll hunt for oxygen and methane, gases that together scream life. The telescope's most haunting discovery might be what it doesn't see. Early universe models predicted a fog of primordial hydrogen lit up by the first stars. Yet JWST deep field images show patches of startling transparency, as if something, perhaps voracious black holes or exotic particles, had already cleared the cosmic mist. Then there's the impossible redshift problem. Some galaxies appear older than the universe itself, their light signatures suggesting they existed before time supposedly began. The likely culprit, measurement errors or new physics waiting to be uncovered. Either way, JWST is holding a mirror to our ignorance, showing us how much we've yet to learn. Every photon JWST collects is a vote in a cosmic election, tallying which theories live and which get scrapped. Its images of the Carina Nebula's cosmic cliffs aren't just stellar nurseries, they're time-lapse videos of star birth, with jets of gas screaming outward at supersonic speeds. Its detection of carbon dioxide on Europa hints at subterranean oceans churning with chemistry we've never seen. And when it turns its gaze to the Great Red Spot, Jupiter's storm becomes a laboratory for atmospheric physics, its swirling gases a Rosetta Stone for decoding weather on exoplanets. The James Webb Space Telescope is more than a tool. It's a translator for a universe that's been speaking to us for billions of years, its messages written in wavelengths we're only now learning to read. With every new observation, we're not just uncovering the past, we're rewriting the future of discovery, one infrared whisper at a time. Neural networks are the new astronomers, tirelessly scanning the heavens with silicon eyes that never blink. While human scientists sift through data at a glacial pace, artificial intelligence devours petabytes of cosmic information like a black hole consuming starlight. Take the Galaxy Zoo project. What began as a crowdsourced effort to classify galaxy shapes has evolved into a machine learning revolution. AI models trained on millions of galactic images now categorize spiral arms, elliptical bulges, and merging clusters with superhuman accuracy, spotting subtle distortions that hint at dark matter's invisible hand. These algorithms don't just work faster, they see differently, detecting patterns in the noise that human brains are wired to overlook. The real game changer is how these networks handle the universe's most elusive signals. In 2018, a neural network at Lawrence Berkeley National Laboratory made headlines when it discovered 2,000 new gravitational lens candidates, galaxies whose gravity bends distant light into cosmic mirages in mere hours. Human researchers had previously identified just 300 of these rare phenomena after decades of searching. Similarly, at the University of Warwick, AI sifts through Kepler telescope data with inhuman patience, flagging the faintest dips in starlight that betray orbiting exoplanets. Some of its discoveries orbit in habitable zones, worlds that manual analysis might have missed entirely, but the most tantalizing applications lie ahead. Pulsars, those cosmic lighthouses, emit pulses so regular they rival atomic clocks. Yet buried in their rhythms could be anomalies, tiny hiccups signaling everything from passing asteroids to gravitational waves. Traditional analysis struggles with these needle-in-a-haystack problems, but neural networks trained on synthetic pulsar data are learning to spot deviations as subtle as a single misplaced beat in a symphony lasting centuries. The same goes for neutrino detectors like IceCube, where AI sorts through billions of phantom particle collisions to find the handful caused by distant supernova or colliding stars. What makes this partnership between machine and cosmos so profound is its potential to decode languages we don't even know exist. SETI researchers now deploy convolutional neural networks to scan radio telescope data for signals that don't match natural astrophysical processes. Unlike old-school algorithms that looked for narrowband pulses, these AI systems hunt for complex patterns, maybe a star's light dimming in unnatural sequences, or gamma-ray bursts with mathematical structures hidden in their timing. They're not just searching for aliens, they're learning the universe's unspoken dialects. Yet for all their power, these systems have blind spots. A neural network might flag a galaxy merger or an anomalous neutrino, but it can't yet ask why these phenomena matter. That's where human intuition still reigns, connecting disparate dots into narratives about dark energy, quantum gravity, or cosmic evolution. The future likely belongs to hybrids, AI as the ultimate research assistant, crunching data at scales that boggle the mind, while human scientists focus on the big picture. Together, they're composing a new chapter in cosmic archaeology, one where the universe's deepest memories aren't just stored, but finally understood. Listening to the cosmos isn't just about turning antennas toward the stars. It's an act of cosmic voyeurism, peeling back the curtains on civilizations that may never have invited our gaze. The universe hums with radio waves, neutrinos, and gravitational ripples, all carrying whispers of distant worlds. But here's the uncomfortable question: do we have the right to listen? Imagine an alien civilization broadcasting medical data or intimate communications, unaware that a species on a pale blue dot is eavesdropping. On Earth, wiretapping without consent is a crime. Does interstellar distance make ethical boundaries irrelevant, or does respect for privacy extend beyond our atmosphere? This dilemma sharpens when we consider intentional signals. SETI decades-long search assumes extraterrestrials want to be found, that their broadcasts are cosmic hellos, not private conversations. But what if we intercept a transmission meant for another civilization entirely? The equivalent would be opening a letter addressed to someone else, its contents never intended for our eyes. Some argue the universe's laws make everything fair game. Photons care nothing for privacy, traveling indiscriminately for eons. Yet others counter that advanced civilizations might encrypt their communications, embedding ethics into their very technology. The WOW signal's fleeting nature could hint at this, a deliberate one-time ping, avoiding persistent surveillance. Then there's the Pandora's box of discovery. Suppose we decode a message confirming we're not just cosmic accidents, but the engineered progeny of some ancient starfaring race. Or worse, uncover a warning that Earth lies in the path of an impending galactic catastrophe. History shows how seismic truths can destabilize societies. Copernicus demoting Earth from the universe's center sparked existential crises. A confirmed alien signal could trigger religious upheavals, economic panic, or militarized scrambles for cosmic supremacy. The very act of listening carries responsibility. Are we prepared to handle truths that might unravel human identity? The flip side is equally thorny: our own transmissions. Every TV broadcast, radar pulse, and stray Wi-Fi signal leaks into space, a cacophony announcing our presence. METI initiatives deliberately amplify this, targeting stars with focused messages. Critics liken this to shouting in a dark forest, unaware of predators. But silence might be futile. Our industrial fingerprints, radioisotopes from nuclear tests, atmospheric CFCs, already betray us. The universe's memory is unforgiving. Long after humanity's extinction, these traces will drift onward, our privacy forfeited to time. Perhaps the answer lies in cosmic etiquette, a framework for respectful engagement. The SETI Institute's post-detection protocols emphasize transparency and global consultation, avoiding unilateral decisions. Similarly, METI advocates propose international consensus before broadcasting, much like environmental impact assessments. But etiquette assumes mutual recognition of rights, a shaky premise when dealing with intelligences that might operate on entirely different ethical frameworks. A hive-mind civilization, for instance, might view individuality as primitive, rendering our privacy concerns meaningless. At its core, this isn't just about aliens. It's about defining what it means to be a civilized neighbor in a universe teeming with potential minds. Every time we point a telescope or beam a message, we're making a choice: to listen, to speak, to risk. The stars don't care about our dilemmas, but if we're not alone, our actions today echo in ways we can't yet imagine. The universe remembers everything, including how we behaved when we thought no one was watching. The cosmic memory isn't just a collection of data points, it's the ultimate detective story, written across billions of years in the language of physics. Every flicker of starlight, every ripple in space-time, every trace of cosmic dust is a clue left behind by a universe that never stops talking. From the moment early humans carved solstice alignments into stone, to the day LIGO caught the faint tremor of colliding black holes, we've been piecing together a narrative far grander than anything mythology could conjure. What's astonishing isn't just the scale of this story, but how personal it feels. The iron in your blood, the calcium in your bones, these were forged in the hearts of long-dead stars, making you a living, breathing chapter in the cosmos autobiography. This interconnectedness transforms how we see our place in the universe. We're not just observers, we're participants, our very existence shaped by events that unfolded eons before Earth formed. The cosmic microwave background, that faint glow from the universe's infancy, isn't just an artifact, it's the reason galaxies could take shape at all, the gravitational blueprint that made your existence possible. Even the mysteries we've yet to solve, like dark matter's invisible web or quantum entanglement's spooky connections, aren't just puzzles. They're invitations to keep exploring, reminders that the universe still has secrets to share. Technology has always been our translator for this cosmic dialogue. The James Webb Space Telescope, with its infrared eyes, peers further back in time than Hubble ever could, while quantum computers simulate conditions too extreme for any lab. Yet for all our tools, the universe still surprises us. Tabby's star's erratic dimming, the WOW signal's cryptic blip, these anomalies remind us that for every question answered, a dozen more emerge. The cosmic memory isn't a static record. It's a living conversation, one where new voices join every time a supernova flares or a neutron star collides. What comes next hinges on our willingness to keep listening. Future telescopes like the Extremely Large Telescope or the Square Kilometre Array will capture fainter whispers from deeper space, while projects like Breakthrough Starshot aim to send microprobes to nearby stars, turning sci-fi dreams into tangible data. But the real frontier isn't just better hardware, it's fresh perspectives. Maybe the key to decoding dark energy lies in an equation scribbled by a student today, or the secret to quantum gravity hides in an ancient text we've yet to fully decipher. The most thrilling possibility, some signals racing toward us right now could rewrite everything we know. A neutrino burst from an unknown astrophysical event, a gravitational wave pattern that defies relativity, or just maybe a transmission that's unmistakably artificial. These potential discoveries aren't distant fantasies. They're photons and particles already en route, their messages traveling at light speed toward detectors not yet built, awaiting minds not yet born. So while we marvel at how far we've come, from tracking Venus on clay tablets to mapping the cosmic web, remember this: the universe's story is still being written. Every time you look up at the night sky, you're not just seeing the past, you're glimpsing a future where today's mysteries become tomorrow's revelations. The cosmic memory doesn't belong to scientists or scholars alone. It belongs to anyone who's ever wondered, ever questioned, ever dared to listen. And that means the next great interpreter could be you. If this journey through cosmic memory left you awestruck, you're not alone. We've barely scratched the surface of the universe's grand archive. Each like and subscription fuels our mission to unravel more celestial mysteries, from the whispers of neutron stars to the encrypted diaries of black holes. Your engagement transforms this channel into a living observatory where curious minds gather to decode the cosmos together. Down in the comments, tell us which cosmic messenger speaks to you most. Is it the eerie precision of pulsars beating like metronomes across the void? The ghostly neutrino particles slipping through your body right now, carrying tales from stellar explosions? Or perhaps the wow signals tantalizing hello that still haunts astronomers decades later? This isn't just a comment section, it's a star map of collective wonder where your insights might spark the next big revelation. The universe's story unfolds in real time, and you've got a front row seat. Hit notification bell so you never miss when we dive into gravitational wave symphonies, dissect exoplanet atmospheres, or chase the shadowy secrets of dark matter. Because here's the thrilling truth: every discovery we've covered, from Babylonian star charts to quantum entangled black holes, is just the prologue, the next chapter. It's being written right now in the data streams of supercomputers, the notebooks of night shift telescope operators, and yes, even in conversations like this one. So keep looking up, keep questioning, and above all, stay curious. The cosmos never stops remembering, and neither should we.